Now let's see how we can apply the big O function to algorithm complexity analysis. Remember, the complexity of an algorithm is based on the number of basic operations that should be executed to solve the problem defined. And remember, the task we're trying to achieve is based on the size of the input, which we will denote by n, and the number of operations, which will be the complexity of the algorithm and will be denoted by f of n. Consider different problems. For example, let's try to find x in an array. The operation we need to do is compare the value that's being searched, which is x, with each entity in the array, one by one. So the size of the input here would be the number of elements in the array. Or if you consider the multiplication of two matrices that contain real values, then the operation is multiplying one by one the elements of each arrays. So we are multiplying at this time two real numbers in each iteration. And the size of the input here would be the dimension of the matrices. Or if we consider the sorting of an array of numbers, the operation we need to do is comparing two array entities and then moving the elements in the array, switching them. And the size of the input here would be the number of elements in the array. So how do we count the number of operations? We are going to look at first how we deal with loops. Let's first take a simple for loop. The running time of a for loop is actually the running time of the statement block in the loop times the number of iterations in the loop. So in the example given, the loop iterates n times, and the statement block there, here it's simply a single statement, that statement block is repeated n times. Therefore, the runtime would be on. Whereas in the case of nested loops, we have one loop in another. So in this example now, we would have the outer loop iterating n times and the inner loop iterating again n times. So the statement block here would be executed n times n square times. Therefore, the runtime complexity of the nested loops in this example would be on square. How about having two parts, two fragments in a program, this time not nested one in another as we had in the previous nested for loops case, but this time these segments or fragments are coming one after another in a consecutive manner. Let's look at the example here. In the first fragment, we have a simple for loop, which is, as we have studied earlier, on square. So, I'm sorry, it's on complexity. And the second part, the second fragment, contains on square complexity because we have the outer loop iterating n times and the inner loop iterating 2n times. So it has complexity on square. If we look at the complexity of the overall code segment here in part C, the complexity would be the maximum of the two fragments. If you consider on and on square, we know on square is larger. Therefore, the complexity would be on square for the whole segment in part C. If we have conditional statements like the if statement, now we are executing either statement block 1 or statement block 2. When I'm analyzing this code segment, I cannot know whether statement block 1, or statement block 2 will be executed. So the overall complexity of the if statement in this case would be the larger of the two. So again, similar to part C, we are taking the larger one or the maximum of the two statement blocks. Here are some examples. Let's first look at example 1. We have two loops listed one another. The outer loop iterates n times, and the inner loop iterates n times n, in other words, n squared times. So the sum statement here, the statement block, is executed n squared times due to the inner loop, but that O(n) squared complexity of the inner loop here is repeated n times. So it is n times n squared. Therefore, we have O(n) cube complexity for the code segment in example 1. Let's go to example 2. This time, the outer loop iterates n times, but the inner loop iterates I times, where I is changing in every iteration of the outer loop. In other words, in the first iteration, I would be 0, so from 0 to j less than 0, so nothing will be executed in the first iteration. In the second iteration, the inner loop will be executed once, then twice, 3 times, 4 times, 5 times. It will go this way. So it is actually, if you look at the number of times this statement sum plus plus here is executed, it's executed 0 times, once, plus 2 times, plus 3 times, plus 4 times. It goes all the way to n minus 1. Now, if you take the sum of the numbers from 1 to n or 0 to n minus 1, it doesn't matter. The overall complexity of that, if you write that, remember Gauss' law, it would be of the order O(n) squared. Okay? Now, finally, if you look at example 3, this time we have a single loop that's executed n squared times. However, there is a method call here. We're calling a method named compute value with some parameter j. I don't care what it is. And we're given in the question that this method has a complexity of O(n) log n. Now, why is it n log n? It's just given in the question. I don't know why. We don't know the details of that method. But assuming that the complexity of that method is n log n, I'm calling that method n squared times. So the complexity would be n squared times n log n. Therefore, it would be n cubed times log n. So we say the complexity of the overall code segment here in example 3 is big O of n cubed times log n. Once again, remember that big O denotes the upper bound. We don't necessarily have to hit that value. How about searching for a value in an unordered array? Pay attention to the word here, unordered. So the array I have is not sorted here. So I don't know where the element is in the array. I have to check one by one. So if I have n elements in the array, the loop iterates n times. N times I do a comparison. Therefore, the complexity would be simply O(n). Now, if I'm searching in a two-dimensional array of size n times m, the outer loop iterates n times, the inner loop iterates m times, so the if statement here will be executed n times m times. Therefore, the complexity would be O(n) times m.